Thanks, Pete. Yeah, something a bit different for me, machine learning. First, I'll tell you what I'm going to talk about. Machine learning, I'm going to talk about what it is and how it affects us and how it is going to affect us when all these people turn up on our sites. Digital transformation is here, and machine learning is basically a tool that we can use or other people can use for us, and we probably need to understand it. So I'll give you an intro to machine learning, how it's used in geoscience already, and I'll take a look at some geotechnical data using some machine learning techniques. That's a ridge of iron ore in the Pilbara, and it's a project I went to, and someone wants to mine it, but they don't want to drill any geotechnical holes. Why would you? And I'm not saying that machine learning is the answer to that, but I came up with an engineering geological model. Cross sections are always great because you can pepper them with question marks, which is harder to do when you've got a 3D solid you rotate around. I haven't seen that kind of texture in Gem 4D with question marks on it yet, which maybe is something I should suggest to France. But basically, there was a lot of uncertainty, and really the deposit dipped at between 70 and kind of 20 degrees. It's a Proterozoic iron ore deposit, conglomeratic iron ore. So not your typical Pilbara iron ore, but it does have some things that ring geotechnical alarm bells, and that includes shale in the immediate footwall. So after some discussions on site about what was in the footwall and what wasn't, and how solidified it might or might not have been, I said, well, you could find out by drilling some geotechnical drill holes, and the discussion moved on. So I took an approach for escaping level design of flattening the batters so they weren't undercutting the dip of the strata, and you got a design that wasn't a dip slope and included some waste, which didn't make the client overly happy, but there we go. So we continue to have discussions about shales in the footwall, and I went to a whole load of sources of data, as you can in the early phases of a project, and found some old 1X reports, had logs showing there's shale in the footwall, and I used the logs I've been provided by the company that showed there was shale in the footwall, and I did some, looked at the geological maps which said there's shale in the footwall, and that was all pretty comprehensive for me. And then the geo throws me some assay data that he's annotated, and he's looked at the assay data and said, well, you've got the yellow is the ore, and then the material beneath it is silicified. It can't be shale, and he's gone to redo their logging by looking at basically the amounts of different elements within the material, which was a fairly new approach to me. More a traditionalist who likes my geotechnical core. But even to override what had been logged was a bit of an eye-opener. So this got me asking a few questions of myself. Am I using all the available data? Well, I think in this case I am, but for other areas where I work, are there other things I can look at? And there are different ways that I can look at them. So I took a look at machine learning and data science, and that's been around a long time, since around the 1950s, but really it's taken off in fairly recently. Machine learning is basically using computers to generate relationships that help predict variables. Doesn't sound overly complicated. You give a computer lots of data with hopefully a relationship in it. It comes up with a model, and then you can make predictions. So pretty easy to conceptualize at that kind of level. You get supervised and unsupervised machine learning. Supervised, generally you'll split your data set into training and testing components. Unsupervised is a bit more complex and not really the focus I want to talk about today. It's the kind of thing where you could give a whole lot of photos of cats and dogs to a computer, and then it would recognise there's differences between cats and dogs and might tell you that one part is cats and one part is dogs. But it's not really my thing, cats and dogs. Supervised machine learning up here, unsupervised down here, which is more into deep learning and machine learning. But these ones up here, so image classification and regression are the two main models you get. And here you've got things like, you've got, here you need to train it. Your outcome is known, so you need to train data set, and here the computer works it out all for itself. Data science related to machine learning. I've had people turn around and say, but what is data science? And it's something that really we probably all use a lot of the tools for already. It's basically the application of data analysis, machine learning and predictive models to solve challenges and improve business processes. It has a bit of a life cycle, not entirely dissimilar to the geotechnical life cycle. So you have the business understanding. They want something to be improved. You collect some data to do that. You prepare your data, which is probably the biggest bit of most projects. You do some data analysis, come up with some parameters. You throw it into your model. You check the model's working well. You give your model to someone, say to your mining engineer or to your business, and then the business says, well, actually, the ore's not there. We need to change the mine. Let's do it all again. Or they say, well, that model was rubbish. Let's do something else. So it's a cycle. It's not dissimilar to what we know, but really the fundamental thing is making sure you've got decent data and looking at it and understanding it. But data scientists, they are coming into all sorts of businesses. They're not necessarily specialists in your business or in our field. They rely on data analysis tools, statistics and models. They can make some really pretty graphs really quickly, just single lines of code that will, impress you and your managers. They may not have the fundamental knowledge of the subject matter, and they're certainly not likely to have the hard-won experience of the grisly people, many of whom are sitting in this room. So there's some risks in there. So machine learning and geoscience, I went to uni and I lived with a couple of computer scientists in my last year, and they took the piss out of me all the time about colouring in. And machine learning and geoscience, they would just say, is training a machine to colour in for you, which is not quite the case, but so it's already used in a number of areas, used a lot in a number of different areas, especially geostatistics and things like kriging. It's been used more and more, and you can see that this is geoscience papers that reference machine learning, and I think today we've probably had 3 or 4 of the presentations have mentioned machine learning, which is maybe we're on that upward trend as well. And a few examples that are relevant to geotech. So this was one where what they call seismic bumps in Polish coal mines were looked at. There were some issues there, and they produced a data set and gave it to a whole lot of teams to see who could come up with the best model to predict from data in the preceding 12 hours when a large energy seismic event might occur in these coal mines. And that was a competition, and they wrote a paper on the people that won that, which I think was actually implemented. But you read these papers and you see there's things that are lacking in terms of any input of 3D data, like whether there might be geological structures or things that we would think are pretty fundamental. These guys looked at drill hole data, so I think they got some geophysical downhole data and used that to predict where gold assays or gold might be within the drill hole they were looking at. And then there's a good review article that talks about loads of different applications of machine learning in geoscience, lots of them in geophysics, but all across geoscience, which was out this year. An interesting read, and goes through some practical examples if you want to know a bit more. This paper I also found, which really got my interest, predicting slope stability failure through machine learning paradigms, and that sounded pretty interesting. So they looked at a number of different machine learning techniques that had already been published by others, so supervised and regression to predict the factor of safety of slopes. And the idea was you could do this instead of using limit equilibrium or numerical methods. So they had a pretty simplistic slope where they varied the angle of the slope, the strength of the clay, the load on the slope and the setback of the load. And they ran, I think, about 600 stability models to try and come up with some relationships. So this is a nice image from their paper where there's some exciting stuff going on. And this is all the really complex machine learning kind of things that we don't really understand, and it's a bit black boxy. But they looked at the models, they ran these. I'm not sure if that slip circle is constrained there, but they're computer scientists, so they weren't too worried about that. And they came up with some models, and they used them to make design charts, which seemed a bit backward to me. If you can put something into a model and get a prediction, why would you then go to a design chart? But their comments were that, talking about limit equilibrium numerical methods, there are some defects in those methods, and there's a difficultness to determine the rational mechanical parameters, for instance. I think we can all agree it can be hard to determine your parameters, and that makes them cumbersome to implement. And another disadvantage, this is for the managers, that slope stability is related to the time and cost constraints for implementing such models. So you can save some money, Julian, by having these guys on site to do machine learning for your slope stability, so you don't have to.
What parameters are I using?
Well, you wouldn't use the mechanical parameters because there's some difficultness in obtaining them, so you'd have to come up with different parameters. But they are in the model anyway. But this was, I thought, one of the, not the best model they came up with, but it, pretty impressive R-squared number. And you can see that if your factor of safety is between 5 and 20, the model's doing a really good job. So some comfort there. If you take your manager a factor of safety of -3, he might come back to you and ask you what the hell you've been doing. But that's the kind of thing that makes us laugh, that is a very real risk, I suppose. If you start going down this route, there's some sensibility checks that need to be made, and there's some domain understanding that needs to be in there. And coming back to mining companies or tech companies, you see these things around the place of we need to have all these people in our organisations. And it worries me. And I'm not sure whether this guy here is there, he's the robot that's going to be doing the mining with the shovel, or whether he's the mining engineer / geotech / geo who's going to use his shovel to bash these guys when they bring him a factor of safety of -3. But yeah, it's one to think about. So what I was going to talk about, geotechnical data. So we're all familiar with this. You need to have a certain understanding of your geotechnical data to do design. At the early phase of projects, we rely heavily on diamond drill core. And that's not to discount geophysical sources or whatever. And we're often data limited and much less data than there might be available from drilling. So there might be a lot more data on the ground, but not necessarily geotechnically accessible data. And that's where I thought, well, maybe I can use machine learning to look at whatever is available in this other 90% of the data to try and infer some geotechnical parameters. So the parameters I was looking at, and this is a conceptual study, I'm not going away and designing anything on this or suggesting we don't need to do geotechnical drilling. So I looked at trying to infer some intact rock properties, the block volume, and then the condition of joints. So the two sides of your GSI chart, if you like, and the intact strength of the rock. I had a personal brainstorm on these things, which I like to do, and thought about the things that might influence the intact properties. The same with block volume, a bit more difficult to get from raw drilling data, perhaps. How far you are from faults, axes and faults, for example, and joint conditions as well. And then I thought about geotechnical data. So what data have I got and what can I look at? So you need a training data set, which has plenty of data, which is high quality geotechnical data, and also has this other data which you want to relate it to. It needs to be fairly abundant. You need a fair few points to make these models work. And again, garbage in, garbage out. Third time we've heard that today, so it must mean something. And you need crossover between data sets. So if you're going to try and relate your geotechnical data to assay data, then you need to make sure that you've got assays on your geotechnical core, or it's very difficult to do. And I looked at using measured values rather than geologically logged parameters. That was a decision I made early when I was playing with this. And for the block volume, I used structural models, which are all subject to interpretation. We've all seen structural models which can change quite dramatically for whatever reason. The important thing in these processes is you've got to ask yourself some questions and think about the quality of your data. Is there a bias? One thing that Python and R do is they make it very easy to deal with missing values. You can fill them as 0, you can discount them, or you can fill them in with the average of the mean of a group or the median of a group, or you can fill them in with the row above, or how have you done that? That can have a big influence. Outliers, there's a reason why they cap gold grades when they do block models for resource estimation. How have you dealt with them? Have they been removed or capped? Did you composite your data when you're drilling data? Have you made it all the same size? Are there different interval lengths? Does it need to be weighted? Categorical variables tend to be more difficult to incorporate in some models, although there's tools for doing that. Did you have time series data? That can be, if you had geochemical or hydrogeological data, it can be very relevant. Have you got enough data? And do you have issues with covariance, codependencies? So a good list of questions to take to people when they bring you machine learning models. I looked at a few models. I looked at using regression, basically. So multivariate linear regression. So I think we all know what linear regression is. Multivariate linear regression is to basically B1, y equals B1 plus x1 plus B2 plus x2 to the ith degree. K nearest neighbour, so this is where you would plot your data in how many dimensions you have, and then you'd categorise this data point based on the k number of closest other data points. So in this instance, if your k value was 4, you'd look at the 4 closest, and you'd either assign it the majority number or an average of the closest 4 data points. So you're basically looking for similarity in multi-dimensions and assigning a value, either an average or a category based on that. And then decision trees. So taking making a decision based on the value of a certain variable, and then branching off into different decision trees based on that. And then you get down to leaf nodes, where you may have a whole load of different data points that sit down there, and you can either average them or take the category that's most prevalent in them. So that can be used for categorical or regression as well. And then random forest. So a random forest is basically a whole load of decision trees that are not necessarily optimized, but you split things through decision trees, and then you can aggregate the results from different trees. So for me, there's the neural networks. They're pretty complicated. I can't conceptualize that. For me, these I can conceptualize fairly well in a couple of dimensions, but this random forest is one that's a bit harder to interrogate because it is more black boxy. It's more difficult to see what's happened. The others you can look at fairly readily. So I did some of this. I used the random forest, and don't cancel your geotechnical drilling just yet. So I got some results. On the x-axis is the measured value, and on the y-axis is the predicted value. And R squareds were above 0, so I was quite happy, but they're a lot less than 1. So I haven't quit the day job just yet. So anyway, there's some opportunities to refine those models. I didn't spend a huge amount of time tweaking them and looking at them. And I wouldn't mind getting a few additional data sets to have a look at as well. But I do think, there's some fundamental hypotheses made sense to me that, within that data, and those models were from Arnold, it was in the Pilbara, if you've got a certain chemistry, then that is likely to correlate to a certain strength material, potentially. So there's some fundamentals that make sense. I think there's some, there's some ways it could be used, and it could potentially be incorporated into block models, especially for if you get relationships between how far you are from structural features like faults and fold hinges, and whether that has an effect on your RQD or your fracture frequency. There's no reason why you couldn't run those same algorithms on points in a block model. But also, this may, in terms of strength, give you a different version of the truth, a different version of the block model to test sensitivities or to inform you at the planning stage of projects, I suppose, or the earlier stage of projects. So, just to conclude, machine learning is coming, or it's here. It's been here for a long time. Those non-specialists, the non-geotechnical mining specialists, will need direction from technical people like those in their room. If your manager says he wants to go down that route, it's probably better to be involved than not be involved. If you want to use it on your geotechnical data, make sure you get your confidence in your data. Do to your geotech data what you do to your resource drilling. Be aware of uncertainties and interpretive parameters. And remember the questions to ask. If someone, there's enough uncertainties in our data anyway, you want to know how that's been processed, and these are some questions which might help you try and find out. Use your shovel if you need to. A few references and some further reading there for anyone that's interested. Thanks very much.